Welcome back. The first two problems on the back page are still factoring problems, but this time we're going to factor them using a technique we learned in Chapter 2 called factoring by grouping. Now, when we factor by grouping for polynomials, I think it's easier than it was for quadratics because my first step is just to start grouping. So I'm going to start grouping my polynomial by grouping my first two terms together and my last two terms together. Remember that in that second grouping, if you start out with a negative, put a little plus in the middle to remind yourself you're not multiplying these two groups yet, you're just adding a negative term. I look at the first grouping that I made and I see that they both have in common an x squared. So I factor out an x squared, and when I look at what's left, I have an x minus 3. Plus, I go to my second group, and I do the same thing. I look for what they both have in common. Well, these are both divisible by negative 16. When I look at what's left, I have an x minus 3. Now, this was still all y equals. That y equals hasn't gone away. When I look at the two groups that I've created now, I see that both groups have an x minus 3. So I'm going to factor out an x minus 3. And when I look at what's left, I have an x squared plus negative 16. So I'm just going to say minus 16. And it's still y equals. Now this is not quite factored because I noticed that this x squared minus 16 is now a difference of squares. So I can continue factoring it just like we did on the last problem, where I can do x minus 4 and x plus 4. So now it's fully factored. I can set it equal to 0 and I can identify all of my zeros. I should have 3 of them because this started out as a cubic. And when I set each one equal to 0, I get 3, positive 4, and negative 4. So I did indeed have 3 roots. All right, look at number 4. This problem is also factoring by grouping, but I want to give you a chance to try it. So follow the same pattern that we did on this last problem. Go ahead and pause the video and restart it again once you've had a few minutes to try it. All right, let's see how you did. So I'm going to start the same way I started the last one, where I'm going to group my first two terms. I'm going to group my last two terms. I don't have to worry about putting a plus in the middle because there's already one. I go look at my first grouping that I made, and I see that they both had in common a 2x squared. When I look at what's left over, once I've factored that out, I have an x plus 3. Plus, I go to my second grouping, and hopefully you saw that what they both had in common was a 50. Times what's left over is x plus 3. The y equals is still in front. Check that you haven't dropped it off. Now that I look at my two groups, hopefully you saw that both groups had an x plus 3. So I'm going to factor out an x plus 3, which means my other factor is 2x squared plus 50. Now, if I want this thing to be in factored form, this 2x squared plus 50 is not quite there yet. So the first thing I might consider doing is taking this 2 and factoring it out. I like to put the 2 in the front. When I've factored it out, all I have left is an x squared plus 25. Now looking at x squared plus 25, we should recognize this. This is a sum of squares, which means that I should be able to factor it into x plus 5i and x minus 5i. Now that I've fully factored it, I can set my function equal to 0, and I can figure out where my 3 zeros were. I know there needed to be 3 because this was a cubic. Looking at each piece, it looks like one of them was when x was negative 3, and the other two were plus or minus 5i. All right, so we have one big topic left to talk about when it comes to zeros of polynomials, and it's something called the multiplicity of zeros. So first thing we're going to do is write down a definition. So the multiplicity of a zero refers to the number of times its factor appears in factored form. So the multiplicity of a 0 refers to the number of times its factor appears in factored form. So as an example, let's write down this function and we'll talk about the multiplicity of each 0. So let's say that it's y equals x times x plus 1 squared times x minus 2 cubed. Now, if I were to expand this, what it would really look like would be x showing up 1 time, x plus 1 showing up 2 times because it was squared, and then x minus 2 showing up 3 times because it was cubed. So when looking at each one of these factors, the number of times they show up tells me the multiplicity. When I look at just x by itself, as a root, the root is x equals 0, and because it only occurs once, its multiplicity is 1. Now, instead of just saying multiplicity of 1, another way that we could describe it is a single root. It just shows up once. When we look at this middle term, x plus 1 squared, well, as a root, its root is x equals negative 1. Its multiplicity would be 2 because it shows up twice, and we would call this a double root, which we'll graph in a minute. My final one, x minus 2 cubed, well, its root would be x equals 2. It has a multiplicity of 3 because it shows up 3 times, and we will be calling this a triple root. So how exactly does the multiplicity of a 0 affect the graph? Well, when we have a multiplicity of 1, because we refer to that as a single root, what that means is my function is going to cross the x-axis linearly. So it almost looks like it's crossing it like a line. When we have a multiplicity of 2, which means we have a double root, that means that my function bounces off the x-axis. It doesn't actually cross through, it just touches and then comes back down or goes back up, depending on which side it came from. For a multiplicity of 3, which means we have a triple root, my function is going to dance through the x-axis. So it does cross through the x-axis, but it's not going to do it linearly. That's how we're going to distinguish between a single root and a triple root. So let's go ahead and try to graph the function that we had written out just a minute ago when talking about multiplicity. I see that it has a root at 0, negative 1, and 2. So the first thing I'm going to do on my graph is to show myself where those different roots are. I'm not going to worry so much about how they cross through the graph. I'm just going to worry about showing that I have 3 x-intercepts. Now, in order to figure out what this graph really looks like, I need to go back and think about the end behavior. Now, remember, the end behavior depended on the leading term. I don't want to FOIL all of this out, but imagine if we did. We would have an x squared, we would have an x cubed, we have an x. If we multiply x times x squared times x cubed, we would get a leading term of x to the 6th. Because it's positive, both ends of my graph should go up. So I know that at negative 1, which was a double root, my graph is going to bounce and come back up. I know that at 0, I have a single root. So my graph had to have a maximum somewhere in order for it to come back down. Notice it crossed through linearly. Also notice we don't exactly know where this maximum is. We just know it had to have a smooth maximum because it's a polynomial. When it comes back up through 2, it's not going to do so linearly. So the way I'm going to show that is I'm going to kind of have it flatten out and continue going again. So it's almost like it dances through the x-axis. So we call this a triple root when it dances A single root, when it just crosses right through like a line, it's linear. And then a double root is the one that bounces off and just continues the way that it came. So now let's actually put this into practice. So look at example 4. We're going to use multiplicity and end behavior to sketch this graph. The first thing I like to do is just mark out where my x-intercepts are. So I see that one of my x-intercepts is at -3. You could even make a note to yourself, this is multiplicity 3, so we know that when we graph it, it's going to have to dance through that point. X equals 1 is also one of my x-intercepts. It has multiplicity 1, so it's just going to cross through linearly. And then x equals 2 has a multiplicity of 2, so it's going to cross through, or sorry, not cross through, it's going to bounce off. So let's go ahead and plot our 3 x-intercepts. Now, in order for me to actually sketch this graph, I need to think about the end behavior. So if we had FOILed this out, we would have an x cubed times an x times an x squared, which leaves us with 1, 2, 3, 4, 5, 6. But because I have this -2 in front, my leading term is -2 x to the 6th. Because I have an even degree and a negative coefficient, I know that my end behavior should be going down on both sides. So now I can start actually making this graph. Because -3 is my most left x-intercept, I know that my graph is going to start out down here. Now, as I approach -3, remember it was a triple root. So I want it to flatten out at -3 and then continue. So it does a little dance through -3. It doesn't just cross linearly. I know that 1 was a single root. So somewhere in here, this graph had to have a maximum. I don't exactly know where it was, but it had to have a maximum so that it could come back down. In order to get to 2, which was a double root, there had to be a minimum. And then because it's double root, it's going to bounce off and continue. So again, I have a triple root that dances through the x-axis. I have a single root that goes through linearly. And I have a double root that just bounces. I don't know where these relative maximums or minimums are. All I know is that they occur somewhere between the x-intercepts. All right, so on to our last example problem. Here we're given a polynomial with a single root, a double root, and a triple root, and we want to try to write it in factored form. Because I wasn't told anything about the vertical dilation, I start my factored form with an a. And then I'm going to fill in a single root at 2, meaning it only gets a first power, a double root at 1, meaning it gets a squared, and a triple root at -2, so it gets a cube. The reason I was given the y-intercept is so I could plug it in for x and y. So I'm going to plug in that x is 0, where y was -31. And now we get, 32, now we get to simplify. So I'm going to simplify each piece individually. So 0 minus 2 is -2. 0 minus 1 is -1, but when I square it, I get a 1. 0 plus 2 is 2, and when I cube it, I get an 8. So keep in mind order of operations. Now all of these things are still being multiplied. So if I multiply them together, I get a times -16. If I divide both sides by -16, I get that a was 2. My final step is to go back and write p of x with the a that I just found. I'm going to keep it in factored form, although it is okay if you keep the multiplicities on top rather than writing them all the way out. So now you've written an equation with multiplicities in factored form. The rest of your class time today can be spent working on homework. We will revisit zeros of polynomials on Monday. Otherwise, have a great weekend.